So, what if the cleanest, most responsible-looking code you ever wrote was actually a secret time bomb, just waiting to crash your entire system? I know, it sounds totally backward, but it's a really deceptive bug that catches even the most careful developers. We're going to unravel this exact mystery by following one programmer's journey right into a coding crisis, and it's a journey that reveals a fundamental truth about the Go language.
Meet Ethan. He's a junior developer, and right now, he is staring at his screen just completely baffled. He's written this batch processor that, on the surface, looks perfect. It's clean, it follows all the best practices, but it is failing catastrophically under any real load. You can almost feel his frustration. He's doing everything by the book, but the system is just screaming at him that he's doing it all wrong.
And this is the stark message staring back at him from the terminal. For any developer, this is a dreaded sight. It's a classic sign of a resource leak. But Ethan is absolutely sure he's been closing everything he opens. So what is really going on here? Where is this leak hiding in his perfectly clean code? Okay, let's break down the problem. Ethan needs to process 1,000 log files. So he's written a pretty standard loop that goes through each file path, opens the file, and then, being a good developer, he immediately uses a defer statement to schedule its closing. In his mind, he's being super efficient and safe. And this slide really shows the huge disconnect. On the left, that's Ethan's mental model. Open a file, close it, move on to the next one. Simple, sequential, totally safe. But on the right, well, that's the harsh reality of what's happening. He opens file 1 and tells the system to close it later. Then he opens file 2 and tells the system to close it later. The files aren't actually being closed at all inside the loop. So this is where Eleanor, a senior engineer, steps in. She takes one look at Ethan's code, and she immediately recognizes the classic defer in loop trap. She explains that the problem isn't a bug in the loop itself, but it's a fundamental misunderstanding of one of Go's core features. And this right here gets to the absolute heart of the misunderstanding. You see, in Go, defer doesn't care about a single loop iteration. It doesn't see these little blocks of code, it only sees the entire function that it lives inside. So when Ethan defers a close, he's not telling Go to close the file at the end of the loop's current run. Nope, he's telling it to close the file when the entire function is finally done. So what's actually happening under the hood? Well, with each and every loop, another deferred close call gets pushed onto a stack. Think of it like you're just piling up IOUs. By the time the loop is on its 1,000th file, there's this massive stack of 999 previous IOUs that still haven't been paid. The resources are just being hoarded, not released.
And that is the scale of the problem we're talking about. Not 1 or 2, but 1,000 files being held open in memory all at the same time. Every single one of them is just sitting there, waiting for the parent function to finally finish its work so that the giant stack of deferred calls can finally unwind and execute.
And the effect is this relentless climb. The number of open files just keeps going up and up and up until bam, it smashes right into the operating system's hard limit. And that's when the system just says, nope, no more, and triggers that dreaded crash. The trap has been sprung.
So how do we escape this trap? Well, Eleanor shows Ethan a surprisingly elegant solution. It's a really common pattern in Go called the loop closure pattern. And the cool thing is, it doesn't fight against defer, it just gives defer a much, much smaller container to live in. And the solution is actually pretty simple once you see the code. Okay, this is the big aha moment. On the left, we have the original problematic code. On the right, we have the fix. Notice the only real change is wrapping the body of the loop inside a func this, func this. This is what we call an anonymous function, or a closure. It's basically a function with no name that we declare and execute immediately, all in one go. So why does this simple trick fix the entire problem? Well, it's because we've given the defer statement a brand new, much smaller scope to play in. Instead of being tied to that large outer function, it's now tied to this tiny, temporary, anonymous function. And since that little function begins and ends entirely within a single loop iteration, the defer is forced to execute right away.
And here is the payoff, plain as day. That tall red bar of doom is gone. In its place, we have this small, stable, happy little green bar. With the fix, the program only ever has one file open at any given moment. It opens one, processes it, and that anonymous function makes sure it's closed before the loop even thinks about starting the next iteration. No more resource hoarding, no more crash.
So Ethan's problem is solved, but the lesson here is universal for any developer. This isn't just about defer or even about Go, really. It's about understanding scope, the
the context in which your code actually executes. It's all about knowing the lifecycle of your variables and your resources.
So let's just boil this all down to the key takeaways. First, remember, defer is a function-level tool, not a block-level or loop-level one. Second, if you use it carelessly inside a really big loop, you are basically asking for trouble. And third, that anonymous function trick, the loop closure pattern, that is your secret weapon for taming defer and making it work on your schedule, not its own.
I love Eleanor's final piece of wisdom here. It's such a perfect metaphor. Think of your function's scope as a container. If that container is too big and you just keep piling things into it, like, say, hundreds of open files, it is eventually going to overflow. The solution is to use smaller, more manageable containers.
And that leaves us with a final thought, right? Code doesn't always behave the way it looks. Ethan's code looked clean, it looked responsible, but it had this secret, destructive life of its own. It's a great reminder for all of us to not just write code that works, but to truly understand why it works. It really challenges us to ask what hidden behaviors are lurking in our own projects.